Hi, I thought I'd revisit this TL494 PowerPoint controller for heating water. Prior designs were probably a little hard for most people to build who aren't really experienced with this. So I've come up with something that uses a few more parts, but it's far simpler to understand. We still use the TL494 board. There's three components that we have to work with. The top one is a diode. The diode you just pull up. That's the Lockout Diode. If this thing ever turns off, it won't turn back on unless you remove all power. So we remove that diode so that doesn't happen. Just below that is a capacitor. On the back we put one in parallel. I got two in here just to get the right value. And right above the capacitor is a resistor. We pull up one leg and we add a 1 mega ohm resistor in series with that, and that sets your timing. The two center pins, you do a solder bridge between those. That gives you two ground pins coming out. These are DuPont connectors. These are dirt cheap, really nice to connect things up. Put a blob of hot melt glue or something to keep them together. Don't glue on this side with the metal pins or you won't get the thing apart or back together. But these things only have about 3 strands of wires. If you said like, hey, I'm going to save some money, I'm going to buy a long one of these and just cut it in half, that's not going to work. You try and solder onto these wires, they will break very easily. They need the strain relief, so we use the females on one end, the males on the other, and solder right to the tips of them. That works out pretty good. Use very little heat. This plastic will easily melt. So this is using a boost converter, but you don't need to use a boost converter if you have 60 volt panels, you know, 230 grid tie panels in series. That would be all you'd need to run this. You have the same capacitor bank. This is I got 30 volt panels and they're in parallel because I have a lot of shading in my backyard, and what happens is the performance is a little better if I have them in parallel, but elsewhere I would just put panels in series. So this is the change. You know, you still have your adjustment pot, and instead of the TL431 I just use a standard transistor, any NPN with the gain of about 150 or more, and I do a little emitter resistor for feedback, a little filtering on the input. Here's the Zener supply. What we do is we take, this is 75 volts over on this side, so we drop through this resistor, and we use the relay as part of the resistor. And what happens is early in the morning, when the sun's just coming up, you're producing very little voltage, very little current, and you get into this range of around, you know, 6 to 10 volts, where this TL494 board, this does not have any undervoltage lockout as the board is designed, and it'll start oscillating. It'll turn on these FETs in a linear region, and they'll just sit here and cook. And they'll keep cooking because they keep getting turned on, and as the panel current increases, it just increases the current going through these. The voltage doesn't jump up any. So what we do is we use this relay, and when you reach about that 13 milliamp current, which you need to ensure good operation of the whole system, the relay closes, and then we power up the electronics. So here we're at 148. Like I say, it's a cloudy winter day, and I have a lot of shading. You can see it'll go up to 150. It'll go down to 96. The voltage stays the same. I mean, just keep watching that while I talk. And that's the beauty of this. It's very fast. So here is the schematic. Here's your board. You got pins 1, 2, 3, 4, 5, 6. 2 center ones are ground. Ground those up around where the FETs are. You have a 12 volt supply. If you have a 24 volt system, you could use a 12 volt regulator and just power this thing all the time. It only takes about 10 mA to power it, so that's no load at all, and then you don't have to worry about putting in a relay or anything. But we have the standard voltage divider. You have to play around with these numbers a little bit. A little filter capacitor. Here's the feedback to make it more linear, and you'll feed about 5.6 volts. That's the transition point for this board. The board has a 5 volt regulator built in for stability, and this is the voltage you have to transition at. This 12 volts has to be a rock solid and very well regulated. You just can't attach it to a battery, because that'll vary your voltage point an awful lot. But then you're driving 2 FETs. Now in mine, I put a little jumper in the back between 13 and 4. Had to cut this trace between 13 and 14, and that puts the outputs in phase. So these FETs both turn on at the same time. As it comes from the factory, it'll turn on this FET, and then it'll turn this one off, and then turn this one on. It alternates back and forth. That dissipates half the power in each FET, and the FETs are cheap. I want you to double them up anyway, and so just buy some extra FETs and put them in parallel, and you can do the alternating pattern. There's things you can do with the alternating pattern, like operate a relay to control the water heater if you want. So there's reasons to do both. And for the power supply for this thing, I'm dropping down. I'm at 60 volts, 2K resistor, and it goes into this little small relay here. It's about 1.5K in resistance. You have your 12 volt center, a capacitor across the relay, keeps it from coming in and out really quick, and then we do some filtering. And here this is the contacts. We turn this on, and it powers the board and this other regulator over here. So let's show you the typical waveform. This is our 5.6 volt signal that we're looking at. It's a little bit of a sine wave, but it's a very small percentage. And when this green is down low, this is when it turns on. This is that little spike there is the dead time. That's between the 2 cycles. So this would be one FET turning on, and this would be the other FET turning on, and they make this big section here. It works great. As you can see, we're up at 230 and the voltage is still around the same. It just keeps it there. Now we can flip this switch and we can turn it on and off. This is where you put your thermostat. I like these little, these things are like $3.5 shipped. They'll give you a reading. Only bad thing is it's in centigrade. If you're in the US, blame Jimmy Carter, you don't know. But this is a nice board. You can put time delays in it. You can put the temperature within better than a half degree. $3. It has an open relay contact that can go right there. There's some other ways we can do this. Now, I want to show you, we're just going to short out these FETs. So we're at 255, and we can turn this down, and it goes down to 50 watts with a equivalent direct connect. So this really works. And most of the day you have some clouds, things aren't ideal, you're never going to produce the maximum amount of amps. So this is the only way to really match things up. Now, if someone wants to build one of these, I have a bunch of these 1200 microfarad 200 volt caps I can sell you pretty cheap, and I can provide some of the other little parts. You know, ordering a bunch of little parts on eBay is expensive, so I can give you the pots and capacitors and a bunch of the resistors and make it a little bit easier build. But this is it. I think it's very doable. You know, there's only one transistor, you know, and a few other little parts. So thanks for watching, and I hope you try this.